Good afternoon, good evening, ladies and gentlemen. Welcome to another series of online lessons. If you haven't already, please subscribe to the channel, leave a like, comment, and share. Now, in today's lesson, we are in complex analysis, and basically, we are going to look at sequences. So, by the end of this lesson, you should be able to understand what a sequence is, and you should be able to understand the word convergence. Okay, you should be able to understand what the word convergence means, and you should also know how to solve this question that we have here, which asks us to show in two ways that the sequence, which is this sequence here, converges to -2. Okay, and hopefully we'll do this question as well, but this will be our priority. Then we'll move on from there. So, what is a sequence? What is a sequence? Well, a sequence of complex numbers is simply a function. So, a sequence is simply a function whose domain is a set of positive integers. So, there is a function. This function has a domain of positive integers and has a range which are complex numbers. So a sequence is simply a function. A function, we can have a function f of x. This is a function. We also have an. This is also a function. Fn, kn, these are all functions. And basically in each of these functions, f of x, we are replacing in positive integers, which are numbers from x is equals to 1 to infinity. And what we're doing is when we place in a value here, we see what it will give us. So when we place in x equals to 1, what value are we going to get? F of 1. When we place in x is equals to f of 2, all the way to infinity. Okay, so we are replacing in values in this function all the way to infinity, and we see what we get. So for instance, even an, we are replacing in values from n is equals to 1 all the way to infinity. When n is 1, we're going to have a1, comma a2, comma a3, all the way to a infinity. Okay, so basically that is what a sequence is. And these numbers that are produced here, which are called the range or the image of a function, all these are complex numbers. So 1 is also a complex number. 2i is a complex number. 1 plus 3i is also a complex number. Those are some examples. Okay, so now what does it mean for a sequence to converge? So this is the definition. What does it mean for a sequence to converge? Simply, if we can find the number at infinity, or if the number at infinity is finite, is a number that we can count, then we say the sequence converges. So simply, if the limit as n approaches infinity of a sequence, so as we are going to infinity, if we can find the number that exists at infinity for this sequence, if we can find the number that is at infinity, then we say the sequence converges. So simply, if limit as an as n approaches infinity of n is equals to L, and if L is finite, we can count L. It can be a complex number or a real number, but L has to be finite. It should not be infinity, and it should exist. So if L is finite and exists, let me put exists, then an converges. Okay, then if L does not exist, if L does not exist, if L is equals to infinity, or L is undefined, then we simply say the sequence diverges. Okay, so those are the two terms, converges. L is a finite number and it exists, then an converges. If L as n approaches infinity does not exist, L equals to infinity, or L is undefined, then the sequence diverges. So since we are taking the limit for us to find whether the sequence converges or diverges, we have to recall all those principles that we were using in calculus to compute the limit. So now let's look at the example that we have. All right, so we have this question. Let me just erase every marker here. Okay, so this question asks us to show in two ways that the sequence, this converges to 2. So what they are basically asking us is to show that limit as n approaches infinity of Zn should be equal to -2. So they want us to show in two ways that this sequence can be equal to -2. So what we'll just do is we just take the limit as n approaches infinity of the sequence, and we see how we can get 2. Okay, so we'll try this method. So we take limit as n approaches infinity, then we put in, we have -2 plus I -1 to the power n over n squared. And this is basically a function, so we're just going to replace in infinity. So we have -2 plus I -1 to the power infinity over infinity squared. We'll see -1 to the power infinity will be alternating between -1 and +1, -1 and +1. So it will be alternating between -1 and +1. So this one clearly makes this sequence to diverge. Okay, so this will be alternating between -1, +1, -1, +1, and this part here over infinity. Remember, the approach from the left hand side should be equal to the approach from the right hand side when you're taking in the limits. And since this approaches alternates between -1 and +1, it makes the sequence to diverges, which diverges. Okay, so this one diverges when we take in the limit directly, but they want us to show that this one will converge to -2. So what conditions should we put in for this sequence to converge to -2? So the first condition, we'll look at this. First of all, we know that limit as n approaches infinity of -2 plus I -1 to the power n over n squared can be written as, we can split the limit. So we can write the limit of the real part, which is limit as n approaches infinity of -2 plus limit of the imaginary part. So n approaches infinity of I -1 to the power n over n squared. So we know that we can split the limit like that. So this is a limit property. What we're going to do is we're going to find each of these values using certain conditions. And we know that, so the first condition, we know that limit as n approaches infinity of -2 will be equal to -2 because we have no n in here. So this is what we call a constant limit. We have nowhere to replace n, so this will simply be the number itself. Okay, but what about limit as n approaches infinity of I -1 to the power n over n squared? So this part, we want this part to be 0, so that on this part we know that the answer is -2. And if this part is 0, will only remain with -2, and we will answer the first part, which is converging to -2. So how can this be 0? Okay, how can this be 0? Well, this can be 0. So we're saying limit as n approaches infinity of I -1 to the power n over n squared approaches 0, or it can be 0 if this sequence, which is an, is equals to I -1 to the power n over n squared, converges absolutely. Okay, so this can be 0, which is what we want, so that when we put 0 here, what we're going to remain with is -2. If this converges absolutely, what does it mean to converge absolutely? To converge absolutely means if we take limit as n approaches infinity of the absolute value of an, okay, this will be equal to the limit as n approaches infinity of the absolute value of what is here, which is we can factor out the I, so the I can come outside here. Then we have -1 modulus to the power n over the modulus of -2. Okay, we see that what we're going to have is I outside, then here limit as n approaches infinity of the modulus of -1 is just +1 over this modulus will just be n squared. And when we put in infinity here, what we're going to have is I times the I outside here times 1 over infinity squared. Now, what is 1 over a very big number? 1 over a very big number approaches 0. So this would be I times 0, which will be equal to 0. So we see that if this part converges absolutely, this will be 0. Then what we're going to have is 0. Therefore, the limit as n approaches infinity of -2 plus I -1 to the power n over n squared, which can be written as limit of negative of uh, of -2 plus limit as n approaches infinity of I -1 to the power n over n will simply be equal to, so this part will be -2 plus this part will be 0, then which our final answer will be -2. So this is the first condition for which this sequence can approach -2. The second condition, which is condition number 2, again we're going to consider limit as n approaches infinity of -2 plus limit as n approaches infinity of I times -1 to the power n over n. So now, again, we know that limit as n approaches infinity of -2 will simply be equal to -2. Then secondly, limit as n approaches infinity of I -1 to the power n over n approaches 0 if n is an even number. Okay, this is a positive even number. So if k is greater than 1, where k is an integer, okay, this will approach 0. What do we mean? So look at this. If n is an integer, so we're looking at -1 to the power 2. This -1 to the power 2, that will be +1. negative 1 to the power 4, that will be positive 1. Negative 1 to the power 6. So if n is an integer, this will approach 0, which is what we want. Okay? And basically what we're going to have is limit as n approaches infinity of I negative 1 the power n over n squared. So there's a squared here. I've write it here. This will basically be equal to limit as n approaches infinity. So if this is an even number, what we're going to have here is just positive 1. So we're going to have I times 1 over n. If n is an even number, okay, and k is greater than 1 and k is an integer, so we're going to have that. And basically, if that is the case, then limit as n approaches infinity of I negative 1 to the nth over n squared will be equal to, when we put in 1 over infinity, this will basically be equal to 0 for n is equals to 2k, where k is greater than or equal to 1 and k is a positive integer. So if this part is 0, so let me zoom out. Okay, so for this part is negative 2. So simply limit as n approaches infinity of negative 2 plus I negative 1 to the power n over n squared will simply be equal to limit as n approaches infinity of negative 2 plus limit as n approaches infinity of negative 1 to the power n over n squared. So now this part will simply be equal to negative 2 plus this part will simply be equal to 0 for n equals to 2k. Then k is an integer. And basically what we're going to have is negative answer. So that is basically how you're supposed to approach that question. So these are the two conditions that you write there.